My name is Spencer Freebairn. I'm going to try my best to give a brief overview of the 4-bit microprocessor that I implemented in Logisim. I've loaded some instructions into the processor that I'm going to run before I explain things. Here's a close-up of the output, and I'm going to go ahead and run the operations that I've pre-programmed. Okay, and you see that it works. As you can see, my processor closely resembles the block diagram that we were provided for this project. I'll go ahead and explain the various components quickly here. We have a clock that drives a counter. The counter is a up counter that increments from 0 to 255. That's used as an address to select one of the pre-programmed operational codes that we have in our PROM. The PROM passes a value to the instruction decoder, and it also passes 4 bits of data to the multiplexer here. The instruction decoder is output onto a bus of 8 pins, and those are wired to various other components in the processor. We have a display that will display various characters, a register that is used to store values in memory, an arithmetic logic unit that performs operations on that data, and then it outputs to a multiplexer which selects data from the PROM, or it selects the data from the arithmetic logic unit and sends it to the register. I can go through these really quickly here. We have a 1-bit register which stores 1 bit, and it can either keep outputting that stored value or it can save a new value. 4 of those are combined to create a 4-bit one-word register, which we'll use later. And we combine 2 of those into one circuit to create a 2 4-bit word register. It will take 4 bits as input, and this write decoder will select whether and which of these registers will keep that value. That is found right here. And then in the ALU, I told you we'd see one of these 4-bit registers again. That is down here as an accumulator, so whatever value is output from here, from the operation of the ALU, can be stored in the accumulator. And then the MUX, really quickly, pretty simple. These are inputs from the PROM, these are inputs from the ALU, and we use this control pin to select which of those we want, and we will output those. And those are output to the register, which can be written to. Now what we're really interested in is the actual operation of this processor. I don't have time to go over exactly how these work, but I will try to demonstrate it as quickly as possible. I'm going to show you the software subtract to begin with. What we want to do is we want to subtract 3 from 4. So to do that, we need to create the 2's complement version of 3 and then add that to 4. So we're going to use the ALU to manipulate 3. So first we'll load 3 into one of the registers, and what we're going to do is we're going to use the exclusive OR function to flip all of the bits. So instead of it being 0, 0, 1, 1, we're going to make it 1, 1, 0, 0. So we're going to load F, the value F, into register 0, or 1, 1, 1, 1, and then we're going to do the exclusive OR operation, which will flip the bits. We'll save that to register 0. And then what we're going to do is we need to add 1 to that value to get the 2's complement. So we will load the value 1 into register 1, and then we are going to add those 2 together, and we're going to store that in register 0. And then what we want to do is we want to add 4 and that 2's complement version of 3 together. So we're going to load 4 into register 1, we're going to add them together, store it to register 0, and then we're going to output that. Oh, nope, we're going to store the value 3 into register 1, because you need to get the ASCII value, the ASCII number, we need to do 3 and then the number that you want to display. So we already have the number we want to display in register 0. We're putting 3 in register 1, and then we're going to output that, and we will run that, and you get the value of 1. Great, so we've done that. Now what we're going to do is we're going to clear everything out again, and we want to do the hardware subtraction. I'll quickly show you the hardware that I added to make this possible, and then we'll take a look at the actual code that we use. So back in the ALU, you'll see that we have this 2's complement converter. It will end up converting whatever input comes in on the B inputs to the 2's complement version of that number if the negative selector pin is selected as a 1. And we'll take a look at this really quickly. So the way this works is you have a number that's inputted, and if the, like I said, that negative selector pin is at a 0, it's just going to output the same number. But if we turn on the negative converter, then it will output the negative number. The bits are flipped, 1 is added to it, and you get the 2's complement version. So now I'm going to show you the code necessary to perform the hardware subtraction. So you load the negative number, or the number that you want to be negative, into register 0. So we're going to do that with 1, 3. And then you load the other number into register 1. And then you perform the hardware subtraction. So I added a new opcode to do this. It's a A0. And then you save that, and then you load 3 into register 1 for the ASCII code, and then you display it. And we'll run that. And as you can see, we have the result, which is 1.